And the next problem that I want to cover together with you is small windows. Now, of course, if you have any requests for problems to solve, please do let us know. I'll see it in my side chat here. And so let's take a look at our small windows problem. The small windows problem looks like this. Let's say we have some sort of grouped analysis or rolling analysis, and the window sizes are very, very small. And the number of windows that we're going to look at, or the number of groups that we're going to look at, are quite large. And so let me show you a little bit of sample data, and you'll see what I mean by this. Here, I've generated a little bit of synthetic data representing, say, website telemetry. And it'll take a while for this data to be generated. There's quite a bit here. But you can see here I have something on the order of 2.5 million rows of data for different IP addresses and different points in time and different pages that they may have clicked at on a particular website. And I might want to ask questions like, who was my most frequent visitor? Who clicked the most? And if you think about that analysis, it's pretty straightforward to formulate. I'll group by the IP address, and I'll just do a group by count. Well, let's think about a little bit of the background and theory for this problem so we can understand why it is that group by count might not be what we want to do in a case like that. Similarly, if I wanted to, for example, look at every window of size of say 5 elements, like I want to sort this by the date, maybe pull that date into my index, and I want to see, within every overlapping window of 5 visits, what's the most common page that people visit? Again, I'd have a very similar problem. The window size is relatively small. Well, consider this. When we're working with NumPy or pandas, we want to avoid crossing the restricted computation domain boundary. We want to keep as much of our work as possible in NumPy or pandas, and we don't want to have any looping at the scale of at the scale of the data itself. And so if we are doing a group by on some data, and let's say the data looks like this, kind of simpler, where it's just A, B, C, D, E, F, X, Y, Z values, but we have a lot of them. Well, if you think about it, when we do a group by with a mean, let's do a group by on this index. Here, we're providing pandas, and let's do a group by on, that's good. Let's see whether, and that should do a mean of, and it didn't as type, it categoricalized the underlying data here. So we'll just do a group by like that. So here, if we do a group by mean, you can see it computes the mean. It gives us a result that has 3 rows, 1 for each of the groups. We know that the group by ag style and the group by ag style and the group by transform style tend to be the ones that we prefer because we know that this helps pandas allocate exactly the amount of memory that it needs ahead of time. And this is similar with any one of these built-in functions. When we think of something like group by mean or group by cumulative sum, more or less they'll map to either an aggregation, that is, producing 1 row for each of the grouping characteristics, or a transformation, producing 1 row for each of the original source rows. Well, in either one of these cases, pandas knows exactly how much memory to allocate, and in the case of something like a group by mean, we use a built-in function, pandas even has the ability to drop all the way into the restricted computation domain and figure out how to do this as fast as possible. Guys, if you think about it, up to this point, you really haven't computed anything yet. You've just told pandas what to do. Group them and compute a mean, and there's enough of an intermediation here where pandas can apply whatever optimization it wants. In fact, it's the case that something like a group by mean or a group by ag passing the string mean or a group by ag passing mp.mean or whatnot, they're all more or less the same because whatever the case may be, pandas can see that you are asking for this grouping and this aggregation, and it has all the information it needs in order to figure out the most effective way to compute this. However, there is a meaningful difference between .mean, .ag_mean, and a .ag where we pass this a lambda and do the mean here. And the reason why there is a meaningful difference here is, fundamentally, Python functions are opaque. There's enough dynamic behavior in Python that we never really know what g.mean actually means until we execute this code. tools like NumPy make certain reasonable assumptions about where that dynamicness may actually show up and where things might be swapped out. But there's a lot of monkey patching that could happen in between each individual one of these .mean calls. Somebody could monkey patch the NumPy ND array or the pandas.Series, the pandas.DataFrame structure, and swap out what .mean means in between these computations. And in general, there's not really any way that we know that that didn't happen. It's unlikely, but we don't know for certain. As a consequence, Python functions have this aspect of being somewhat opaque. Because these are opaque, most tools won't bother to try to statically analyze this code. So pandas isn't going to bother to say, oh, it's just a lambda that calls .mean on whatever the group is. I'll statically analyze that and make it identical to the first two. They'll see a lambda, they'll see a user-supplied or user-defined function, and just dead stop, there's nothing I can do. Which means, in these two cases, the actual aggregation operation is happening inside the restricted computation domain at pandas or at C speed. In this case, even though the result will be the same, the underlying operation is happening at Python speed because pandas has no choice but to say, look, you gave me a UDF. I don't really know what to do with it. I'm just going to call this function for each one of my groups. However, if we think about what the penalty there is, well, there's only 3 groups. So we necessarily know that this function will only be called 3 times. The problem with iterating at the pure Python speed really is about iterating not over the structure of a data frame, like how this breaks into groups or what the columns are, but iterating over the data. If I had 5,000 rows, I don't want to call a Python function for every single row, which is the case if I did something like s.apply. But I'm actually OK with calling a Python function for every unique group, as long as the number of unique groups is relatively few. In this case, I'm only going to call this function 3 times. And so even though these two and this one are materially different, in fact, the performance here, I may not actually see much of a difference. However, if I make the cardinality of the number of unique groups much higher, as it is the case with our IP address data, because you can think any possible IP address, well, then we're going to run into trouble. Because how many IP addresses would there be? Well, assuming that we don't take into account, as part of at least the simulation of our data, that some of these IP addresses aren't valid or whatnot, at the upper bound, we have this many, 256 raised to the 4th power, possible IP addresses minus some of the blocks which aren't valid. So we've got 4 billion possible groups. And even if we say, OK, only half of those are in use, we've got 2 billion groups. We're going to call a Python function 2 billion times. Well, this is a problem. And unfortunately, we're somewhat limited by what we can do about this. We need to find some contortion that allows us to push the computation into the restricted computation domain. If this is a rolling analysis, not a grouped analysis, we may have a couple of tricks. One trick that we may employ is, given our underlying data, what we might do if we wanted to do some analysis that was rolling on a fixed window size, like an s.rolling2, well, this is actually not too bad for us to do in the restricted computation domain, even if there is a UDF that's provided, because what we know is we can go into the underlying NumPy values of this structure and use something like NumPy stride, NumPy.stride as window. Gonna forget the name of this. Stride tricks. There we go. And I got to remember what this is called. But we can use or we can construct this ourselves from as-strided, or we can use the sliding window view and operate on the raw NumPy data. So we could say from numpy.lib, stride tricks, import sliding window view, and take the underlying values, do the sliding window view of the underlying values, like that. So we get now a sliding window view of every 2 values overlapping. And then all we have to do is figure out how we take that UDF and at least decompose it into something that is NumPy applicable, which, as you'll discover, is a little bit easier to do than you might expect. Because, for example, if this ag is something like take the group and figure out what percentage contribution or this is, or what the sum, dot sum is pretty easy. But if you want to do something like a transform on this, and you wanted to take each of the values and divide the value by whatever the sum is for that window, so you see what the relative contribution is, something like that. Actually, you can't do the rolling transform easily like that. So here, let me think of an operation that you can do. But if you wanted to do like an aggregation here, and you wanted to do something that was multiple NumPy operations, like I guess here you might do something like, we'll sum this up, and then we'll subtract from this, the mean of the value, whatever the case may be. In pure pandas, you have no choice but to express this as a UDF. But if you can get the raw NumPy data, well, you could just take this ND array and perform the operations you want on that ND array, and you can push this into the restricted computation domain. So it's not uncommon for us to find that, and we'll do this on the axis 1. So that gives us the first operation on that axis, and then here's the second operation on that axis, and then we just subtract them. And we can get effectively what we would be forced to use a Python UDF to do, but we can actually express this in the restricted computation of NumPy. It comes up quite often. And so one of the approaches we can deal with if you have very small windows is drop down to the raw NumPy data, and if possible, reconstitute the UDF in terms of broadcasted operations on the raw NumPy data, and then resituate the data back into the series. This is going to be a little bit ugly, because what we'll have to do is we'll have to reconstitute this series and grab the index, grab its index back up. But, sure, it's a little clumsy, but we get to the answer in the end. Let's do this as data like that. And here we need to take this result, and we'll have to actually add in one nan, because remember, so we'll have to go from, or strip it off from the beginning to the end, just because we're missing one window here. So there you can see we do something like that, or we might have to put in a nan at the beginning manually by stacking this together with a nan value. Whatever the case may be, we'll have to reconstitute this series. We can do that. If it's the case of a grouping operation, well, we're going to have to use a custom window function likely, or we're going to have to do some sort of dropping down into Python. So there really aren't many easy answers for this whenever we deal with very small windows. The other place where small windows might show up is if we do something with an expanding. Whenever we're doing an expanding, we're looking at 1 row, then 2 rows, then 3 rows, then 4 rows, then 5 rows. And as a consequence, we are necessarily performing the operation, the window operation on this expanding, on the scope of the data itself. This is why when you look at expanding in contrast with something like rolling or something like groupby, you're actually much more limited in terms of what you're able to do, because in fact, an expanding with some sort of UDF is not guaranteed to be any faster than just doing something like, if we have some UDF here, applying that on the windows themselves in a Python loop. And in that case, we really need some contortions in order to, for example, synthetically create a NumPy and D array via stride tricks in order to mimic an expanding structure. It's possible to do. It is a giant pain. And so our answer for this problem is a little bit clumsy. What we're going to do in order to try and answer things like, which are the most common users, is we may first want to take this data and maybe sort by that index. We might want to do maybe a NumPy operation to identify where the boundaries of each of these are, where the groups are. And the groups themselves is something which, actually pandas can do pretty effectively. If we just group by this thing's index, and here let's name this index as well, and let's actually store this data so we don't have to pay the cost of generating it. So we'll store this data. Okay, there we go. And here, we can, here we'll just do a, what is this? We want to rename the axis so we know what that index level is called. It's our IP address. We could group by the IP address. We can operate on each of these groups individually in a Python for loop, and it's not going to be that much different in terms of the speed as if we just perform like an ag or apply operation. If we do something that's built in, we might do like a .count here, and in this case, this allows us to solve the problem. But fundamentally, what we have to be careful of is if we're doing some sort of apply operation, if we're doing some sort of ag or transform operation with the UDF and figuring out how to dismantle that. And so there really isn't a good answer for this other than this is one of the cases where you just have to drop down into the NumPy layer in order to be able to do this effectively or be willing to write some Python code or maybe some NumPy code. This is a fundamental limitation of pandas, group bys with UDFs or rolling with UDF on very small windows.